For those just joining, we will get started in just a few minutes. This is the Amazon Braket workshop for QC Hack 2022. If you are watching live from Twitch, you can find a link to the Zoom either on the website or on Discord. It'd be better, you get a better experience if you join the Zoom live. But for those who are watching the Twitch recording afterwards, files will be made accessible to you. All right, hello everyone. If you haven't heard me say this before, we'll get started in just a minute or two now. If you're watching the Twitch recording live, you can find a Zoom link on either the website or the Discord. And if possible, please come over to the Zoom live. Twitch participants who are watching the recording will get the full experience, but in order to get the files we'll use for the workshop live, it's better to be in the Zoom link. All right. Hello and welcome to the Amazon Braket workshop for QC Hack 2022. We're thrilled to be collaborating with Amazon over the course of this hackathon. And today we'll be hearing from Juan Monero, an Amazon Braket Solutions architect who's been with Amazon for 8.5 years. And also Tyler Takashita, an Amazon Braket Solutions architect as well. So they'll be presenting an introduction to Braket, a fully managed quantum computing service designed to help speed up scientific research and software development for quantum computing. Now, for those attending live, files will be provided in the Zoom link. For those who are going to watch the recording, don't worry. Check the description for a link to a GitHub repository for the same content. If anyone is watching live via Twitch, you can tune into the Zoom by clicking the link either on the Discord or on the website. If you have any questions, don't hesitate to post them in the chat. And then without further ado, I'll pass it off to Juan.
Thank you very much, Rom. Nice to meet you all. Thank you for joining us today, wherever you are in the world. I'm based in Austin, Texas right now, so it's a very nice afternoon here. We're gonna have fun today, hopefully. We're gonna be setting up together our environment that is gonna give you a chance to play with Amazon Braket, our quantum computing service here in AWS. We will do that first of all, and then we will get hands-on, and we will cover some theory. And throughout the session, please feel free to ping questions. I have my colleagues here in the chat, mixed between the audience, that will be able to help me with questions that might come up. Also, feel free to interrupt me, ask any questions you have, okay? Let me start sharing my screen. I have been having technical difficulties. Hopefully my computer will not die on me when I do that, but let me try once again and share the agenda for today with you. All right.
That looks good to us, Juan.
Awesome. Thank you for that confirmation. Let me go back here so I can see you. So we are going to do a hands-on workshop. That's the agenda for today. First of all, what I was saying, we are going to do the introduction. We are going to set up the environment. I want you to launch a few things that we are going to leave running in the background because take a few minutes to create. And then we will go back and do the actual theoretical introduction to quantum computing on AWS. We will do a demo, and then we will keep working on those notebooks together. So the first thing I'm going to do is to share a link with all of you. And I want you to go ahead and go and click on that link and follow the instructions with me. Let me see, where's my chat window? Here. That's the link for the event engine. What I'm going to do is open it here as well. It should take you to a window like this. Can you see a web browser window there?
Looks good to me.
Perfect. Thank you. We are going to go ahead and click on one-time password, or OTP. You should see something, even though I don't see it. Interesting. All right, let me see what's going on. Doesn't seem to be working. Okay. And event engine. Okay, that seems to be working better. So let's do it this way. You can try to go to that link first if the previous one didn't return anything meaningful to you, like it happened to me. And from there, you can paste the hash ID for the event that I'm going to paste as well in the window separately. space that hash window. What you should see is a sequence similar to this one. When you click on the first link, you see this window, and then you can paste the event hash there, accept the terms and login. Then select the one-time password. I will send you an email address when you enter in the next window your email address there. Click on send passcode. Then when you check your email, this is just an example, you will get a code that you have to come and put back in this window, this passcode. And after that, you should see a window that will give you access to the AWS console. It should be in windows like this. It's a dashboard. I'll give you a few seconds, a few minutes. It shouldn't take more than a minute for you to receive your email. Please, if you have problems accessing to this or you are not seeing the same as I'm describing, please let us know so we can help you. What we are trying to do here is to basically give you access to AWS so we can start launching a couple of things. Okay, let's see. Cannot parse state. Curious to know if that happened when you did it in 2 steps or everyone is getting the same error. Okay.
Go
ahead.
I'm running into that as well. Everything works up to the point where you click, you accept terms and login, and then immediately after clicking email one-time password. It's white screen except for times New Roman 12 point cannot parse state or not. So actually, it seems to be I don't know if everyone is able to do this, but trying to log in with a retail Amazon account might work.
Well, not ideal, but if that works, yeah. Sorry about that. I don't know what happened there. I see.
I didn't copy down the code. I didn't know that we're supposed to do. Maybe I probably not the only one. Maybe we can start over so we know what we need to do step by step, particularly the logging, the process.
I can start from here. So if you go to dashboard.eventengine.run, /login, or just the root URL, you will get into this window. And then the event hash is the one I posted over there. I'm gonna recover it here again and put it again.
Right. I mean the one that say you cannot see, but we can see. At that moment, I didn't know I should copy down what you cannot see, but we can see.
Oh, I see. So what you want to see is my screen, I guess, right?
I don't know. I think that was the initial step. I didn't know I should copy down. So I think I probably not the only one miss that point. And I think if we miss that first point, then we miss everything following.
Right. Okay, so let's start from a fresh window. Let's go together. Let me open a private browser window.
Thank you.
Absolutely. Thank you for pointing that out. We're gonna type here dashboard.eventengine.run. You can see my browser, right?
Yes.
Okay.
And this link is in the chat, by the way.
Okay. Then from there, in this window, I'm gonna paste my code. Put it one more time there in the chat. Accept terms and login. That will take you to this screen. So this is the part that seems to be failing. I'm gonna try once again. The first option is OTP. And yeah, that gives us an error. I'm really sorry. Not the time to troubleshoot this thing. It seems like if you have an Amazon account, Amazon retail account, or Amazon shop
Hey,
account,
Juan?
that will work.
Juan.
You can go ahead, Ty.
Sorry to interrupt. I've created a new one, so I've sent you another event hash. Maybe we could try fresh with that event.
Okay, let me try that. Thank you. We'll close this window and start a new one.
Juan, for those of us who signed in with the Amazon retail account, would it be worthwhile to close that and then try the new event, or would both work?
Both will work if we are able to access, and the experience will be similar.
Great, thank you.
So Ty, this is the one finished in 65, right? This hash.
That's correct.
Thank you. Let's try this new hash that I just put there. Same problem. Okay. So apologies for that. This is something completely unexpected that I haven't seen before. We will need to talk to our event engine team to see why that is not working today. Obviously, me as an Amazon employee, I can access in different ways. It seems like only the Amazon.com domain will work. So if you have some Amazon account, oh, you said that with the retail account worked.
It seems working on my end. So now it's asking me to put my email address. Is that where we are?
Yeah.
Okay.
That's exactly what we want. After this window, if you
Right,
click
right,
OTP,
I'm on this window.
perfect. So when you click in OTP, it should send it should give you a window to enter your email address. And after you put your email address over there and click on send passcode, you should receive an email with a passcode within a few seconds that you have to put in.
Actually, that error message came after I clicked that OTP, then come the same error message.
I see.
Yeah, sorry.
No, thank you. Thank you for letting me know. All right, so just to summarize, and nobody was able to basically reach this window where you can just click on the AWS console, right? Okay, well, that's a bummer. I guess we're gonna have to switch to demo mode. We are not gonna have an opportunity to get hands-on, or you are not gonna have an opportunity to get hands-on. I will go through the presentation and show you how things work in practice. Okay, excellent. Seems some people, okay, some people are able to access to the console. That's good. So we will do both things. I'll provide files and we will do it interactive as well for those of you who were able to access. Apologies for the rest of you who couldn't. What we are gonna do for those who are able to access to the console is the following. Let me see. I'm gonna bring back my window with the console open. And I'll tell you what to do next. Right. I cannot access myself, so there is a window that I'm not going to be able to see, but I will describe it for you. When you access to the Amazon console, it doesn't really matter how it looks like in the body of the main page. but you will see a search button on the top, and there you can type Braket or Amazon Braket. You will see the service and you can click on it. When you click on it and it's the first time that you access, you will see a different window to this one that I'm displaying right now. You will see a window that gives you 2 fields to complete. One of them is the name of S3 bucket, which is the storage unit in AWS. You will be given an option to create a new bucket with a random string that the system generates for you. You can go ahead and leave that by default. And if you scroll down to the bottom of the screen, you will see a tick box with accept terms and conditions. This is the activation of Braket service that you need to go through the first time that you use the service. Just go ahead and do that. Just select the default S3 bucket that is proposed to you, tick accept terms and conditions, and move on to the next screen. And that should take you right here, what you are seeing right now.
That worked for me, Juan.
Awesome. Thank you, guys. Once you have done that, let's go to notebooks. You will see an empty screen here and create a notebook instance. For the instance name, you can name it whatever you please. You see hack, your name, and workshop. The instance size can stay on T3 medium, that is the default one. You could pick any other one, but for the examples that we are going to run today, this is enough. And then you will see that an existing IAM role is selected. You don't need to change anything there. I think it's called team role, if I'm not mistaken, in your screen. And leave the rest of the options as they are, and then click on create notebook instance.
I was able to log in, and what I see right now is a team dashboard, AWS console, or SSH key.
Yeah, so if you click on AWS console.
Okay. Okay. Yes, I did.
Perfect. So that should give you access to the console. I think the next button you have to click, speaking by memory, is in the top left to open the actual console.
Okay, yes, on top left, that's correct. Open AWS console, yes.
Yeah. After you reach the console, you will need to go to the top window where the search button, search control is, and type Braket.
Okay.
And when you do that, you will be able to click on Amazon Braket and accept the terms and conditions of the service and pick the default bucket that is offered to you.
So search window put what? A bracket?
Yeah, you need to type Braket on the
Okay.
top of the screen in the search button.
Okay, got it. Yeah. Okay. On the top one is Amazon Braket. That's
Yep.
the one, right? Yeah. Okay.
That's right. You can click on that one.
Okay. Now shows the getting started with Amazon Braket.
Very good. You can leave the default create new bucket option that you see there.
Right.
And scroll to the bottom and click on accept the terms and conditions.
Okay.
After that, you should land in a screen like this one that I'm showing right now.
Okay, it's turning. Yes, thank you.
Absolutely. Then we go to notebooks, the second link on the left-hand side. And when you are on that window, you can go to the top right and create notebook instance.
Are you talking about that QPU page? I see here D-Wave.
So yeah, in that window where you are right now, go to the left-hand side of the screen, and you will see devices, notebooks, jobs, and tasks. Click on notebooks.
I see here INQ, Oxford, Lucy.
No, so even more left than that.
More left. Oh, okay. I'm not.
The very left of the screen.
Oh, okay. Notebook. I got it. Okay.
Click on notebooks.
Yeah, I did.
And then on the top right, there is a big orange button that says create notebook instance.
Right. Okay, I did.
Perfect. So from there, you just need to give a name to your instance.
Okay, can I just use my own name or need to be some? Okay.
Yeah.
Okay.
It's your personal instance. Leave everything as it is. Scroll all the way to the bottom.
Okay.
And click on create notebook instance.
Okay.
And that's it for the moment. That will start to create an instance that you will see that is in pending state. After 5-6 minutes, you will be in service like the other ones that you see in the screen.
Okay, great. Thank you.
Well, that's no problem at all. My pleasure. When that's been generated, that will set up our environment that is going to allow us to interact with the service. I'm going to go ahead and cover the theoretical part. I'm going to be covering what we do at AWS in quantum computing, what is Amazon Braket, the service that you had a chance already to interact a little bit with, and a few other topics. First of all, I want to clarify that, well, the service was launched. Let me put my screens in order here. That's better. Yeah, the service was launched initially at the end of 2019. And for us, getting into quantum computing was a matter of being very excited about this relatively new technology, but also being very humble about all the technological challenges and the engineering challenges that it poses to build a quantum computer and to make progress in this space. So for that reason, we not only created a service that basically allowed people to type code and send it to a quantum computer, but a whole set of features and tools that cover all the aspects of quantum computing. These are the 4 pillars that you can see in the screen of quantum computing at AWS. We have a research center in California. We also have the Quantum Solutions Lab with our professional services team. We have a network of partners that are specialized in different areas, and we have Amazon Braket that you are going to be interacting with today. That is the actual single pane of glass that gives you access to the computers. The Center for Quantum Computing was created to basically push the boundaries on research and development. We have a lot of people, many brilliant minds on this space working over there, working both in software and hardware development. So things from creating our own quantum computer that we have a project ongoing to do things like error correction and algorithm optimization and things like that. Besides that, we have our professional services team. The previous team that I mentioned to you usually is not customer facing, but this team is. The professional services team is the Quantum Solutions Lab, is a group of professionals that are experts in their fields, not only in quantum computing, but also in machine learning, high performance computing, and things like that. Because what we want to do is to work from the customer problem backwards, sit down with the customer, understand what they are trying to do and whether they think that it could be a quantum problem. And if it is, help them to develop the algorithms and the intellectual property that is going to be valuable for them, usually in the form of a POC that they can use in the future when the machines actually scale and are at the point where it can be fault tolerant and running production workloads. If one day that happens, they will be ready. They will be at the forefront of innovation. So this team is actually working on those things. They are open. So initially a problem that a customer might think is a quantum computing problem might turn out to be an HPC problem instead, or a machine learning problem. So that's what this team of specialists does. Then the partners, this is only in the screen a few of them. Probably if you are participating in this event, you already heard about QBraid, is one of our partners, but there are others that work in different areas of quantum computing. There are some of them are specialized in finance, some others are specialized in chemistry and materials. And when the customer wants to work in a specific area, we can partner them with these companies to work together. All right, Braket. This is the STAR service, right? And we wanted to democratize the access to quantum computers. The main distinction of Amazon Braket is that it gives you access to many different types of platforms, quantum devices that you can use to start building your code, to test your algorithms, and see how they operate or how they work in different endpoints, as we call them. Ideally, you want to start building something. Maybe at the beginning it's something very simple, and you start testing in a simulator. We will see later how Amazon Braket comes with an SDK that contains a local simulator on it, and you can write your code there, see if the numbers make sense, and then you can move into something bigger, maybe a managed simulator that we will be covering. We have 3 of them. You use your managed simulator, and after that, you can basically change your endpoint and put it to run in a real quantum device, and then analyze the results. Everything is connected with the whole AWS set of services, more than 200 services that allow you to do monitoring and raise alerts and alarms and see how the algorithm is evolving as it's getting executed. We are going to see details of all that. Today, the point is to get deeper into actually getting familiar with Amazon Braket, right? So this is what we are going to do. As I was mentioning, Braket comes with a Python SDK and is thoroughly documented. In the link that you have over there, you can find the documentation. And whenever you start playing with this, today or later on during this weekend, during the rest of the event, you can refer to the documentation to see how do I don't know, create a Hadamard gate or create a superposition state, or it's all described there, and you can use it. The SDK is something that you can download and use in your own local environment if you want. So initially we proposed Jupyter notebooks, and it's all managed, right? You access to the web, access to Braket, open a notebook as you just have been doing for the last few minutes. But you can also configure everything locally if you have an IDE that you like, and access to the service that way. That's totally open. The GitHub repository is there for you to download the SDK and start working with it. And by the way, it comes with simulators, as I said. You can even generate noise if you want to on that. We will be covering more of that a little bit later in the hands-on part. This is the architecture. This is how Amazon Braket looks like. On the left-hand side is everything that, or most of the things that you have seen already. The managed notebooks, your local IDE if you want to do it locally, and then the Braket console. You saw the welcome screen, and we are going to navigate more in a few minutes. There you will be able to see your tasks that you execute, the characteristics of the machines, what are the specific components of them, how the qubits are connected to each other, and things like that. The service comes with 3 managed simulators, as I mentioned, and then you have access to quantum devices that are located on our hardware partners' locations. So we go ahead and access to them. You can access to them through Braket when you send your code. And as everything else in AWS, everything is connected. So it's just an Amazon Braket for us is like another service. If you're familiar with AWS or you work with AWS Cloud before, you heard about CloudWatch, S3, or EC2. Those are services that are connected to Braket and you can leverage to do more powerful stuff. Starting from the top, you see there are CloudWatch, where you can see how your algorithm is evolving, the timestamp, and how it is doing. With Event Bridge, you are able to trigger other actions. Maybe you are working in a mixed environment or hybrid environment, and you want to wait for the results of your quantum device to maybe feed that into a machine learning pipeline using SageMaker, which is our machine learning product. So Event Bridge will allow you to write that event-driven type of coding, where you can trigger one thing when the other thing happens, or as simple as getting a notification, for example, when your task or your experiment has finished. Everything that you execute in a quantum device or in a managed simulator will be stored in a text file for your reference with a lot of detail on it. We use Amazon storage, a simple storage service for that, Amazon S3. You just saw how we create our, well, you didn't see it, but you heard how it's necessary to create an S3 bucket at the beginning of the service activation. That's where all your experiments are going to be stored in text files in JSON format that you can go ahead and check later on. And finally, you have very granular access to everything. If you are an administrator and you are concerned about how certain people should be accessing some things but not others, that's all fully configurable. You can restrict access to certain CPUs, QPUs. QPUs, by the way, stands for quantum processing units as an equivalent of the CPU. Or who can do what, or monitor all the activity and have it recorded in a central location. Everything is encrypted end to end, so as everything else in AWS is secured by default. All right, let's go ahead and check a little bit on the first part, the managed notebooks and all that. I think we already saw, yeah, we're gonna give some time to that notebook to launch, so we can go ahead and start working with it as soon as it's ready. Let me talk a little bit more about the managed simulators and the hardware. So we have in total 4 simulators. The first one is the local simulator that comes with the SDK. This is for very small circuits, so just for fast prototyping, as it says there. You write something and you want to see if it works and if you didn't make any mistake, and you can use that simulator to test it. When you want to do something a bit more, let's say big, that will be the next one. The state vector simulator will store the entire wave function of your problem, of your quantum system. So every single possibility of your problem will be stored there, and you will be able to execute circuits of up to 34 qubits on this one. It runs on concurrency, is fully managed and behind the scenes. You don't need to worry about spinning infrastructure or anything like that. You just send it and wait for your result. The tensor network simulators, however, is a bit smarter and more powerful, or I shouldn't say smarter, maybe just different. It is capable to run circuits to up to 50 qubits. And in this case, you want to map your problem as a graph. This simulator is going to find the most effective way to traverse that graph in order to give your answers back. So what that means is that it's not going to store the entire wave function of all the possibilities. Behind the scenes, it's going to run in 2 phases, a rehearsal phase first that will evaluate what are the most feasible solutions. And then it will collapse into returning your results if that's realistic or feasible. Otherwise, it will return an error and it will tell you, make your problem smaller because it cannot fit what you're trying to do. That's the tensor network simulator. And finally, the density matrix simulator, it was the last one that we launched. You can run circuits for up to 17 qubits. And this is our noise simulator. It's based, as the name says, in the density matrix formalism using Krauss operators. So basically, you will be able to generate noise at any point. You can simulate initialization noise, readout noise. You can do big flips or phase damping, whatever you want, but by qubit, in all the qubits, one specific gate, in all the gates, is very, very configurable. Or your custom Krauss density matrices operators that you can configure as you wish with this simulator. Now, the fun part, the QPUs. the quantum processing units. We have at the moment 4 of them. The next one comes in the next slide. You have access to different technologies here. So first of all, on the left-hand side, you see D-Wave. That's a quantum annealer. So basically, usually more qubits. It doesn't need to be necessarily all of them interconnected at once. So allows for a bigger number of count of qubits. It's good for optimization problems and QBO type of problems for binary optimization. And that's one technology that you can use. Hardware-wise, is made of superconducting loops, right? So these tiny metal loops that are at a very low temperature exhibit quantum properties, and you can define the state that way. And you define what is your 1 or your 0 for your qubit. A similar technology in terms of hardware, superconducting loops, is what Rigetti uses, as you can see there. However, Rigetti is a gate-based type of device. It's universal gates, so you have the serial wire, so you can basically present your gates and write circuits with certain depth as much as the device allows. For Rigetti, we have an 80 qubit device. That is the largest that is right now today available and really ready to use for customers in the cloud. So that's as powerful as you can get today. IonQ, however, is also a gate-based and universal gate device, but it's based on trapped ions. In this specific model that is available is 11 qubits, and it's an ytterbium atom where you basically create your ion and trap it using laser tweezers, and then you get your states by rotating the ion one way or another. And finally, we recently added OQC, Oxford Quantum Circuits. It's an 8 qubit machine, also based on gates, and it's a superconducting device as well. Coming very soon, later this year, is the Quera machine. It's based on Rydberg atoms. So in this case, it's not superconducting loops. There are no trapped ions either. You are working with a full atom, or neutral atoms is called sometimes as well. This will be very specific use cases that especially researchers will be able to do with this machine. So we are very excited to see what customers and researchers can do with this one. All right. I think I talked a little bit about S3 and the other integration, so let's move on. With Event Bridge, as I said, you can connect into all other services and basically build something bigger than just running a circuit, right? You can use those results to interact with other stuff. The reason why Quera machine is only specific for some use cases, I don't know 100%. I've been told that it's a little bit of a different architecture, and it's going to be very good to simulate nature, quantum states. So you can call it as a meta device, but it doesn't work exactly in the same way that IonQ machine or a Rigetti machine. But I cannot give you more detail than that, sorry. All right, so this is the architecture. What do I want to do next? Maybe before we jump into the console and start how all these things work in practice, we will take a look to what a shot, a task, and a job are, because you will find them later. So I'm going to cover that now. That way I don't have to go back to the presentation later. So in circuit-based machines, you will, due to the probabilistic nature of quantum computing, you cannot just execute one circuit once and get the result, right? You want to execute it a number of times and then see the probabilistic result, analyze it as such, as a probability. So for that reason, the first thing you do when you write a circuit is to send a number of shots, which are the single executions of that circuit that you send to the machine. Usually you do 100, 1,000, for D-Wave, even 10,000 is the maximum that we allow. And then you read the results and see what are the ones that are most observed, right? Or you play with the observables as well. When you do that, you can group all these things into a task, right? So if I'm writing a circuit like the one you see in the screen there in the first picture, and I execute it 100 times, I want to put all together in a task that will allow me to easily go to the console, click on my task, and see how it is going, or what were the results. So that's the concept of a task, is the series of repeated shots that you execute on a device. And lately, we released the concept of a job, or particularly a hybrid job. This is the case where you know that the near-term applications of quantum computing use QPUs as co-processors to a classical computer, right? It's similar to the way that the GPUs are being used to accelerate the high-performance computing or the machine learning workloads. They work in combination. So you are trying to, for example, reduce the cost function using machine learning. You might want your quantum computer to tell you what is the next lower energy state between 2 points, and pass that information back to your main algorithm in your machine learning algorithm in order to perform the calculation. That's a hybrid job because the quantum computer is working in partnership with the classical computer, and that generates tasks and jobs behind the scenes, right? So in order to tie things up and make it more manageable, we created the concept of a hybrid job, where you execute a number of shots that are grouped in a task, and then you execute a number of tasks in order to get to your final result, and that's a job. That's how we kind of organize the service. And I don't have a slide for billing, but basically we charge the service using these three concepts, right? The shot, the task, and the job. And we're going to see that in the first example in our notebooks. Finally, I want to mention our cooperation with PennyLane. It's very connected to the concept of hybrid jobs, in the sense that PennyLane is a set of libraries that allows you to work on quantum machine learning type of workloads using familiar tools like PyTorch or TensorFlow that you might be used to if you have worked with machine learning before. It's very well suited for this type of hybrid algorithms. And basically, you can install it as a plugin to the main Amazon Braket SDK and use it that way. I'm seeing that question there. How many jobs can I raise with my account? Unlimited. It's just you need to be aware of how those are charged, right? You are charged for the tasks and the shots, but you can run as many jobs as you want. If you're in the free tier, you have 1 hour access for free to the simulators that I showed you just a couple of slides ago. You have 1 hour per month for 1 year as part of your free tier to use it. The access to the QPUs themselves, if you use QPUs on those jobs, then that would come with a charge. But yeah, the usage is unlimited. All right. Yeah, I'm going to finish with this presentation, and let's see how all this works together in the console. This is what I just said, that you have 1 hour of free simulation time per month when you are in the free tier. And you also have credits for research. So if you are part of an institution, are doing interesting things, reach out to us. You can submit an application, and we can get in touch with you to provide some credits for you to get started with your project. So you don't need to get stuck for lack of budget or whatever that is. Okay. We are far from QA and wrap up. QA will take it anytime. Let's go ahead and go to the console. And I'm going to show you a little bit of how all these things ties up together in the console. You see that people are asking questions, so feel free to do the same. If you would prefer to speak, if you are like me, lazy to write, and you prefer to talk, just come up and ask me your question. I'm happy to be interrupted. Otherwise, I get tired. When you access to Braket for the first time, well, first of all, you have to activate the service. And that's the part that, unfortunately, I wasn't able to show you before these technical glitches that we had. But after you activate the service, this is what you see. This is the window where the quantum processing units are stored. And here you can see the devices that I was mentioning earlier. For example, if we go ahead and click here on Lucy, the 8-qubit machine that is based on superconducting loops, you can see a description of the machine. And you also see the topology here. And a very important number, I want you to remember this number, the device ARN. This is the Amazon resource name and that you can use when you're writing your code to send it to a certain backend. This is one of the backends, okay, and it's specified here. You see that the status is online, so the machine can accept circuits at the moment, but the next availability window is in 13 hours. So what that means is that if you send something to this machine right now, it won't be executed right now. It's not going to return an error. It just means that you are sending it to the machine, and it will be put in a queue, and you will go in queue state until the next availability window. You can see here the availability window, the location, and other parameters. Let's take a look to different architectures because this is quite interesting. I'm going to open the Aspen M1 from Braket. This is an 80 qubit machine. And as you can see here, the topology is quite interesting. This machine is available now, so you should be able to get your code back, and we are going to see that in a few minutes when you send something. This is the cost per task and per shot, and this is the topology. As you can see, all these concentric rings are connected to each other in a next neighbor type of architecture. And here you have a calibration window where you can see the fidelity for certain values per individual qubit, as you can see in the left column, but also per pair of qubits. So you can actually, with this device, decide which pair of qubits or which specific qubits you want to use. If we wanted to, we could tell the machine exactly which qubits to use. Let's go back to the devices and check a different one. If I click in IonQ, you see that it's also based on, it's a gate-based device and universal gates, but the topology is quite different. These are 11 qubits connected in a mesh. The calibration window gets simpler because all the qubits are equidistant to each other, right? So, and basically they're all at the same distance, and that simplifies things. There's no machine that is better than others. Some others are faster on the readout. Some others are faster on the execution of the circuit itself. It depends really on what you want to do, especially when the circuits get a bit more complex. And yeah, we are not going to be touching today in annealing and annealing devices, but you can see here how the annealing devices have a much bigger, larger qubit count because the technology that they use is different. This is annealing and more thought for quadratic and constraint binary optimization type of problems, which is a different type of optimization problems. All right, we're gonna go ahead and go in the notebook, and we're gonna start working and playing with the platform. Go ahead and awesome. I see that my colleagues are already answering your questions. That's fantastic. Let me see. I think I opened one before where I had my stuff. It was this one. I hope that at this point everyone has the notebook instance in running mode. It's in service. You will see only one folder called Braket examples, the first one here on the top. I have other stuff, but you should see only this one. As you can see here, you have all types of notebooks and problems classified by complexity and by other topics. You have the annealing stuff over here. Our cooperation with Penny Lane and QML is here. Then the Braket features. We are going to be working with things that are related to this getting started notebook. And that's what we are gonna be doing. I think because we lost some time at the beginning, I'm gonna skip a notebook that I had prepared for seeing the cost of your tasks and your jobs, and we're gonna move directly into executing circuits in the machine. Probably that would be the best thing to do, given that we are almost 1 hour in. So I'm going to give you a notebook, and what I want you to do when you receive that notebook is to download it to your machine first of all, and then come here to the upload option and upload it from your machine. Okay, give me a second, and I'm going to get that notebook ready for you. All right, I just drop it in the chat. It's a Jupyter notebook that you should be able to upload here. I'm gonna do the same. So in case you want to see how it is done, I can show you. Screen one. Upload, as I said. Mouse back here. Oof, okay, seems like Zoom is crashing. I hope I don't get dropped if I have to. Yeah.
Any particular place that we should upload to? Right now, default is a system 32.
You can click into anywhere really is good. So if you can upload it to Braket examples or just in the root folder is also fine.
Okay, thank you.
Absolutely. I put it here inside getting started, but if you go here and upload it right here, maybe it's easier to find. I'm going to click on it. I'm going to open it. I'm going to click here on the chat window in case I missed something. All right. So for those of you who are able to interact with the console, if you don't mind, please type up +1 once you see what I'm saying, please. Thank you, Ricky. Thank you, Christopher. Thanks, Itchel. Robert. Copier. Okay. I'm gonna go ahead and start executing cells here. As you can see here, what we are doing is to import a few libraries. These are just math libraries in order to represent my results. And here are the first SDK, Braket SDK libraries that are imported. Circuit, gate, observable, noise, everything we need. The local simulator is here as well, as you see. And this AWS device is actually the one that is key to access to the quantum endpoints, the quantum processing units. Right, and execute that. You can click on run or just shift enter. That works as well. I like shift enter, but I have to click less. We're gonna build a bell pair that hopefully all of you are familiar with. As you see here, we are creating our circuit. That is our wire. We are attaching a Hadamard gate to bring the qubit to superposition of states in qubit number 0. And then we are appending to that a control NOT gate that operates in qubit 0 and qubit 1, with the qubit 0 at the control qubit and the qubit 1 as the target qubit. And it's as simple as that. And with that, we have created our first circuit, but it's just an abstraction, right? It's just a circuit design or definition. The next thing we have to do is to actually decide in which backend we are going to run our code. The first thing I'm doing is to use the local simulator that is defined like this. And up until this point, I don't need to even have an AWS account or anything. If you download everything to your local computer and you install everything, if you don't mind, my colleagues there in the background, if you don't mind to paste in the chat the link to the setting your own local environment, that will give you instructions on how to do this without actually having to use a Jupyter Notebook. This is to say that you can run in your local simulator and get your results as expected, all locally. In this case, in my Jupyter Notebook. This is running still in my Jupyter Notebook. 511, 489, obviously we run this a few times, we always get different results. Thank you very much, Tyler. And then we can plot our results, so it's a bit more graphical. As we saw, as we expected, when we are in a superposition of states, and also we are doing entanglement between two qubits, what I expect that is that my results will always be either 0, 0 as a final state or 1, 1, approximately 50% of the times for each time. And that's what we are getting here. Once we see that everything is working as it should, then we can go ahead and do a bit more bigger things, as I said before, with the simulators. We are gonna go ahead and move to a managed simulator. In the managed simulator, basically, I have more power, more qubits to play with. I'm gonna define a larger circuit. It's exactly the same as this one. It's the GHZ circuit that you also might be familiar with. It's very good for benchmarking, because when I get a new machine, I can basically bring all the qubits to superposition and see how good is the fidelity of those gates and the accuracy of my results, right? It's a great way to test a new machine. I'm doing exactly the same, defining my circuit, attaching the Hadamard gate to the first qubit, and then I'm leaving up to a variable how many qubits I want to attach to the CNOT gates to the initial qubit, to the control qubit. And that's what I'm doing here. That's how the circuit looks like. You have a print option as well if you want to print your circuit. The thing that is different now is that I'm going to define the ARN, the Amazon Resource Number, for my simulator. And this is the state vector simulator that I'm going to use. If you remember, this is the general purpose one that stores all the results, but I have the option to run bigger circuits with it. So I define my n qubits variable to 15. This is going to be a 15 qubit circuit. And I'm going to run the same del pair. And besides, I'm going to get other observables besides the word count. I'm able to access to more type of results when I use a simulator. In this case, I'm just plotting again the results. And you see, again, all zeros or all ones as expected. So far, so good. A real device which certainly will not give me this type of result, because we have to account for noise, and we are going to see that in just a few minutes. The next thing is the tensor network simulator. I'm not going to be doing anything that involves a graph, and it will be a bit more involved. But I want to show you how, by just changing the ARN, I can basically execute the same code in a bigger circuit. That's exactly what I'm doing here. I'm increasing my number to 50, so I'm still executing my GHZ circuit with 50 qubits and running that. It's going to take me a little bit more time, because this time is a larger circuit and requires remember the rehearsal operation and the collapsing operation that I was mentioning earlier. It came back. And this is, again, the result you get. All my qubits perfectly align in 0 state and 1 state. One thing that you can do in the meantime is to check your results on the file in the S3 bucket that you created earlier. To do that, you just need to go back to your console, and you will see, if you go to tasks, how new task IDs have been created. As you see here, SV1 and TN1, these are the last 2 executions of my simulators that I just ran. The only thing that you need to be careful is that you are in the right region. With the event engine that you have access, you are in US East 1, so you will be able to see these tasks if you go there now. I think your environment does not allow you to change to US West 1 or US West 2 or any other region where Amazon Braket runs. But to see these results, this should be enough. When you click on any of them, for example, let's go to the SV1 results. You see that you have the timestamp, when it started, when it finished, the number of shots that you executed, 1,000 in this case, the device ARN, and then a link to S3, where you can go ahead and download the file with your results. We're going to do that for you to see how it looks like. For those of you who don't have access, but also if you are doing this with me, I invite you to do the same. The result.json will contain the whole detail, the full detail of your experiment. I'm gonna bring my window here. As you can see here, you can see for every single execution of all my shots, what was the result. It's gonna be perfect because it is a simulator, so you see the perfect alignment of zeros and ones. But if you're running in a real device, that won't be the case. I'm gonna go to the bottom to see the summary of my results and comment on that. You see that every task has an ID that you can identify. When you are working with many tasks, you can always bring it using the SDK as well, graphical mode, and identify your task ID, the device ID, the qubit count over here, 15 in this case, the timestamp, and then the gates that you used for your 15 qubits. One Hadamard gate at the top, and then all the control node gates. And the total duration. Everything is there for you to see. Let's go back to our notebook. And probably this is the moment of truth, right? Well, before the moment of truth, before I execute things on the quantum computer, I wanted to show you the actual noise simulation as well. I added this recently, so I always forget that this is here. What I'm doing here is what I was commenting earlier. This is the way in which you can bring your task back if you need it for the last execution. This task ID might be helpful if you are coordinating other tasks. Or for those tasks that take a long time to complete, maybe you don't want to keep your notebook open for 3 or 4 hours while your task is being executed. Or maybe your machine is not in the availability window and the task will not complete until the day after, right? So with this piece of code, you will be able from your own IDE to bring your task back and see how it is doing or if it already completed. The noise simulator, as I said, allows you to introduce noise. In this very simple example, the only thing I'm doing is creating a 3-qubit circuit for you to see the noise. And I'm introducing noise with a probability of 10% of a bit flip. So that means that for the entire circuit, I'm going to be introducing a flip from 0 to 1 randomly 10% of the times. And that gets me a little bit closer what a real device will do. Obviously, it's going to be more complex than that in a real device, but it gives you an idea of the power of this simulator. Apply my noise, define my device, that this time is the DM1, the density metric simulator, call my circuit with my number of shots, and then I just measure the results. And if everything goes well, this time I should see some noise. As you can see here, my 3 qubits. In an ideal world, I should expect 0, 0, 0, and 1, 1, 1, but I see how a chunk of this 1, 1, 1 was taken into the other probabilities, 1, 0, 1, 1, 0, 1, 1, and so on. So I have introduced that bit flip noise in my circuit. Again, I would like to refer to you to the documentation where you can see the different type of noise that you can insert. And this is very useful and very powerful when you have a real quantum device and maybe you have a limited availability window to access to it. But nothing is stopping you to go to that calibration window that I was showing you earlier, see how the machine is calibrated for certain qubits and reproduce that exactly into a noise model, a noise channel that you can apply to your simulation and simulate a real device. So that's how this simulator is very powerful. All right, now it's for the real device. You can see here I'm gonna delete this one, well, too late, but anyway. You see there the Rigetti, the IonQ ARNs. And the first thing we are gonna do is to work with the Rigetti device, the Aspen M1, that is 80 qubits. What I'm doing here is, again, executing a bell pair, getting a few expectation values and counting the results. I haven't mentioned this so far, but I think it's self-explanatory. When you run a circuit, you call the circuit in the first variable and the number of shots in the second variable, 1,000 of them in this case. Now, this is a real device, and you will get the status immediately when you do that with this task state. Then what I can do is to basically call task state as many times as I need to see how my task is doing. Here we see that it's in queued state, because if we go to the console for the Rigetti device, let me go back to Braket. Back to, I'm gonna go to Virginia. I think it's where you have access. You see that the Rigetti device, oh, it's out of it. Oh, okay, yeah, it's afternoon already. PT. Yeah, so the device is not in its availability window, so we are not going to be able to see that task completed. But it's at the moment running. You still have access to the platform for 2 full days. So tomorrow morning, you will be able to see your results if you go to the tasks tab over here. I'm used to do my workshops in the morning, so usually Rigetti is available in the morning, but we have IonQ that is available here now. Let's go ahead and try to do the same in IonQ. What happened here that I don't have device. As you can see, you have to enter your ARN. So I'm gonna give you a few seconds or minutes. Please go ahead, enter your device ARN and execute this. And you let me know in which status it goes, because the machine is active at the moment. I'm curious to see from you guys, what is the status that you get? And even give me the task ID if you are able to find it. Go ahead, I'll give you a couple of minutes so that I can take a break as well or answer questions. Happy to do that. Hopefully, if you have been following, you will be able to figure out what the ARN for IonQ is.
I was able to download or upload, but could not open. Is that I think it was is that because I thought I have Jupyter download on my computer. Is that the reason? Maybe that was on my old computer. You know, the one that you said we can upload. I couldn't.
Yeah, this is the managed environment, so it will be independent whether you have Jupyter installed locally on your machine or not. So in theory, after you went to the notebooks section and you click on the upload button in your notebook, you should be able to upload the file from your local machine.
Oh, okay. Okay, thanks.
Absolutely. I see that someone already is seeing the task in queued state. That's awesome. Probably you might be wondering, well, hold on a second. If IonQ is online and available now, why I'm seeing queued, right? Well, it's processing tasks. IonQ is a busy QPU, so definitely it's not going to be like 18 hours like with Rigetti that is not available right now. IonQ is proactively processing its queue as we speak. So it could be half an hour, it could be 1 hour, but you will see your results eventually coming up. Were you able to, or any of you were able to identify what's your task ID if you need to retrieve it later? Here in the console is straightforward to do as well. See if someone can ping me the task ID that their IonQ device is right now working on, please. There you go. Let me see, is that a task? Yes, yes, very good. So basically you just need to go within US this one here to tasks. And any of these are the previous ones, right? I'm gonna finish it for you now. So you see how it is done. This allows you to copy the ARN of the device. Then I just need to replace it here. A 1,000 shots, everything looks good. First created status, then the queued status, then you will go into running and completed. So because it's executing at the moment, we are not going to be able to see results with the plot as we saw with our simulators, unfortunately. We would be very lucky if IonQ can execute of our task within the time of our workshop. But as I said, these accounts are open there and ready for you for the next 48 hours. So you will be able to see when it completes. Just for you to have an idea of how this looks like, I'm going to open one of them that ran previously. Same thing as with the simulators, you have the S3 bucket where you can retrieve the results.json file. Download the results and open them. And here, well, starting from the bottom, you see the gates that were applied, the observables that we requested, the timestamp, number of qubits, and the other technical parameters, basically. The task ID, the schema that was used for the machine. In the vendor-specific documentation, you can read about the schemas if that interests you. I'm a hardware freak, so I always like to see those things. These are the measurement probabilities. As you can see, it's 00 is 46%, 11 is 51%, and a minimum part goes to 01 and 10 as noise in this case. As you can see, it's less than 0.1%. This is why these machines are still in a very primitive state. We still need to count for these errors when we do our calculations and when we execute our circuits. If you think on a digital computer, that would be unthinkable nowadays, right? That a transistor fails 0.014% of the time. That wouldn't be something that we would accept, right? These machines are still at this moment of maturity. Hopefully, these errors will continue going down and down as the technology evolves. Okay, that's that. In the next cells, what I'm showing you there is exactly because you are not able to see the results yet right now, is to check what is the status of your task in a bit more involved way. You can basically use the states that the SDK provides to you to add some logic and say, okay, if the task is completed, show me the results and plot them. But if it's not, if it has failed or it's canceled, let me know as well. And that's what this piece of code is doing here. The next cell is doing exactly the same thing for IonQ. It's telling you that your task is queued at the moment, as you saw, and hasn't been finalized yet. One last thing, when you start writing more complex stuff, you might want to see the compatibility of your gates, right? You have Oxford quantum circuits, Rigetti, IonQ. This is something that nobody else offered to you these days. So you think about the possibilities. You can write a generic piece of code that executes a circuit and then see how the different fidelities and response times and machine rewiring happens in different backends. In order for you to write a piece of code and forget about what is the machine that is running behind the scenes, you can check what gates are supported for each device. We strive, whenever we add a new machine into Amazon Braket to make it as compatible as possible with things that already exist. And we work hard with the hardware providers in order to provide a clear understanding of what are the gates that are supported. With these commands that you are seeing, you can see the gates that are supported across all devices. This is our own SDK, and it will apply to the simulators. And then these are the gate sets for Rigetti, IonQ, and Oxford. As you see, the common rotations like SY or Z or Y, they are common to all of them, but also C0 or Hadamard gate, that those are common. And then each device has their own particular gates. But at the end of the day, if you think about it, you can basically use basic rotations on the qubit to build any gate that you need. So that allows you to write code once and execute many times in different devices. This is what we mean when we say that we are democratizing, or we want to democratize the access to quantum devices. Very good. This is for the notebook. This is all I had for you in terms of hands-on. Since we still have some time, I'm gonna pause here to see if there is any other question. I can still show you a couple of things in the console, but before I do that, I want to check with the audience. If you are completely sleeping at this point, or you find this interesting and have any question. Tyler, do we have a survey by any chance?
Yep, give me a second.
Tips to run variational. We have notebooks that you can get started with. If you go to your, really any of them.
Sent you the survey one.
Thank you. My mouse is here. I will answer your question in a second. I'm just grabbing a survey that I want to give you. I'm going to cover now, if you are still interested, on how to interact with the rest of the AWS services. But in the meantime, if you don't mind to answer that survey, it will take literally 30 seconds. That will help us to improve. Thank you. Yeah, so Tyler just pasted there the Braket examples GitHub repository. You can access on that public link, or you can also access from inside your instance notebook. Here you have hybrid quantum algorithms, right? And so to run variational, you have some examples to get started, right? You have some QAOA here. And also, I believe we have VQA. For chemistry, a couple of examples of VQE as well for variational. It's more than a notebook, as you can see here. It's almost like documentation or a manual, but it explains concepts, and then it gets you started from scratch on how to write your code, represent your Hamiltonian in the machine, and execute your code. So my recommendation would be that you start over there. It's how I learned personally. So. Oh, Robert, that's an excellent question. I totally feel you. Yeah, it's a lot of information out there, and it can be a little bit daunting sometimes, right? It's important to master the basics because this technology is not like any other cloud technology. I don't know, like serverless or containers or things like that. It's good to know a little bit of linear algebra to understand the qubit rotations and things like that. I would say trigonometry is also important, but those two things are not especially difficult, right? Sometimes it's doing a bit of a refresher of your high school math, and it will come back all to you real fast. There is a few good resource a couple of resources there. But I would say start from the math and then practice with very simple circuits and try to anticipate what the final state is going to be. What I'm trying to say is that you saw what we did, right? We created a circuit and we created one gate and then append more gates to it. So you can, once you have a clear understanding of what a qubit is, you can apply one gate and think what the result is going to be after you apply that gate. At least that's the way my mentors that might be laughing at this point told me to do. And I think it's very useful because I personally, I'm not the type of guy who can read a book for 6 hours straight without actually see how it works. So a little bit of theory and a little bit of practice with simple notebooks. The getting started folder here in the Braket examples is quite good because goes step by step from a very simple circuit. Also for the penny lane examples are quite good. You can load the penny lane library and see how the concept of variational works as well from that perspective using those libraries. I hope it helps. I also want to say that we are there. Those are Tyler's and my what is it called? The name of the chat application that we are using for the event. Anyway, our handles are there if you want to reach out to us.
Sorry, I was on mute. Discord.
There you go. How do you know that this is free? Okay, how do you know? Because you don't have to enter a credit card at any point in time. Probably that's the best way to know that that is free. These accounts are generated by us. The code that you entered basically means that the account is sitting in the AWS side, and you can use it for the next 2 days. And then for the same reason, they will get deleted automatically. So if you are saving stuff or files or anything like that, make sure that you keep a local copy because everything will be gone. Feel free to post your questions there. One thing I wanted to touch because I like this topic is the integration with the rest of the AWS infrastructure or services. I mentioned tangentially earlier the Event Bridge service that you can use. And there's a pretty neat feature in terms of the integration of Amazon Braket and Event Bridge. When you are running a circuit, as you see it right now, it's in queued state. You don't want to be on your notebook refreshing that cell every 5 minutes or every 1 hour until it's completed, right? Event Bridge allows you to create a new rule that will basically send you a notification when the task has completed. And we can do it this way. Create a rule with an event pattern. The event is going to be our quantum task. I pick the AWS services. Sample events. I'm in the right place. This is not the right place. Oh boy, this has changed already. There you go, event pattern. For event pattern, I'm gonna pick Amazon Braket as a service. And then I can select the Braket task state change. So basically, that is telling me whenever the state of my task change, if I'm in queued now, whenever it changed to completed, send me a message. And it could be an SMS or it could be an email, right? And this is where you pick your target here. You can pick an event bus. This has changed as well. No, AWS service. It's been a while. So you pick AWS service and then you select, for example, SNS, that is the system, the simple notification service from AWS. And from SNS, you can create a topic I don't have any topic created here, but basically if you go to the SMS console, you could enter your mobile phone or your email address and create a new topic and link it here. So that way, whenever the task changes state, you will receive a notification automatically that everything has completed, and you can go ahead and pick your file. In the same token, instead of sending a notification, as I was explaining earlier, you could wait for the list of zeros and ones that the file is going to return and process that way using a Lambda function, using this event pattern architecture that I'm showing here, and feed it into something else, maybe a hybrid algorithm or something like that. All right. Feel free to play with all these features. They are available for you. And let us know how it goes. We're going to be available in the chat for you to ask us questions.
That's great. Juan, is there anything else you want to cover, or should we call it there?
We are good to go.
All right.
Sorry, one thing, Juan. We will be providing new accounts for this weekend for the hackathon.
Oh yeah, sorry, I forgot about that. We will be this hash, the current event hash is going to expire on, is it tomorrow, right?
I believe this evening.
Exactly. So from Saturday, you will have to enter another hash in order to continue working with the platform. But we will be providing that in the chat, so you have it. And when you see that everything tears down and you don't have access anymore, you just need to use the new hash and use the same procedure in order for you to access. Thank you for that, Ty.
Fantastic. All right, Ty, Juan, we appreciate you taking the time to lead this great session today. Like you said, if anyone has any lingering questions, please post them in the Amazon channel on the Quantum Coalition Discord. This recording will be made available later on Twitch, as will the files, if you want to go back and review anything. Thank you everyone for participating in the QC Hack 2022's bootcamp. Our next event is Continuum Intro to TCAT at 5 p.m. Eastern later today, about half an hour. I hope to see you all Saturday for the hackathon, and otherwise, have a great day.